Okay, I think it's 9 o'clock. We can start. So, yeah, it's pretty sad that this is the last day of the school. Like I'm really enjoying Nikita providing me various points of reference in his previous talk, and so I can kind of incorporate them into my lectures. So, so we will talk about rigidity in a minute. But in Nikita's lectures, one object that was prominently appearing in the last two lectures was a partition, or in fact maybe R tuple. So forgive me if I take there was an R tuple of partitions lambda, and there was some sort of interaction, and that had to do this R tuple of partitions lambda had to do with the moduli spaces of bundles, instanton sheaves, something that live on a plane with two coordinates x1, x2, which a torus was scaling with weights epsilon1, epsilon2. And so at the end of his lecture yesterday, what happened is that a certain defect was introduced along one of the lines, and so then it had to do. But there's also another direction. This all fits inside 4 dimensions very nicely. There's another direction in which one can go, and one can let this object stack. So this will be still kind of epsilon3 direction. And one can let this object stack in this direction. So this will be some partition. Maybe I'll draw, I don't know. Let me draw some simpler partition so that not to worry too much about it. There was this was a partition lambda, but now lambda will be this object here. And there will be this 3-dimensional thing, which is, somehow. It's like in Professor Schlossman's lecture, except in his lecture, this thing was growing up, and you can rotate this picture. Does that make sense? So if you slice it, it's a sequence of partitions that each fits inside the other, but eventually they all stabilize in partition lambda. This is supposed to be infinite. This leg is infinite. And R tuple, so one such object by the same argument as we somehow thought about this partition as representing various monomials. These guys here, so this object here, this was really one partition was a torus fixed point. In the Hilbert scheme of C2 points. Right? By the same argument, if you bring in one more monomial, monomials in one more variable, this would be this whole picture, this 3-dimensional picture. This is ideal. It corresponds to ideal. Now in the ring of polynomials with 3 variables. But it's not of finite codimension. It misses all the points that go, all monomials that go in this direction. They're all not in the ideal. That clear? So this is ideal. First of all, it's a point in the Hilbert scheme of now curves. Right? So what does it mean? It's an object of dimension 1. It's not the point, it's an object of complex dimension 1. And this particular ideal is this corresponds to some fattening of the x3 axis. Okay. So this is right? So this goes the equations that define this ideal. The monomials. For example, all monomials of x3 they will be sitting here. There will be this x3, x3 square, x3, 3, and so forth. Right. So previously, so these are all functions on the axis itself. And previously they had to terminate, but now they never get into the ideal. So this is this ideal something of dimension 1. That makes sense? And so an R tuple of this such object is a torus fixed points in. So R tuple of flat objects, this was a torus fixed point in bundles of rank R on the plane, right? So this is in sheaves. Well, I'll write sheaves of rank R on C3. And as such, it's an object. This belongs to the subject to the field of DT theory. In a sense, DT theory in general has to do the old DT theory has to do with counting things on threefolds. Counting curves on threefolds, counting points on threefolds, counting bundles on threefolds. So this is. And so now, if we form a generating function, like, except I think it's sacrilegious to denote the elliptic modulus of elliptic curve by a letter other than Q. And so I'd like to keep Q for that. So we need some new variable to count the boxes. So I think I had the variable Z as an argument of Krichever genus, but I think it's maybe we'll use some other variable for that today. So maybe we'll count the boxes. So we count these boxes, count these objects we somehow form. So we write some kind of partition function of a bunch of partitions. So maybe this partition, some other partition, and so R tuple of them. And then we have variables, we may call it Z, maybe T1, T2, or A1, A2, A3. No, this is not. A C1, C2, C3, and then A1, so forth, AR. This is an R tuple of partitions. And then this is the where this variables, like in Nikita lecture, they're assigned to this the assigned position the same exact same way. These are the weights. I think you denote in Q1, Q2, Q3. So I think the notation in Nikita's lecture that this is like Q with a cross, this is Q with 1, this is Q with 2, and this is Q with 3. Well, right, but anyhow, I want Q to be parameter elliptic curve. So with all due respect, I will not use this notation when everything is Q with some decoration. Right? The parameter of the elliptic curve, that's for, well, anyhow. Yeah, we'll talk about it. What? Yes. Anyhow, so that the what I was gonna say. So this is the so this will this is function with the weight when you sum. You know what do we say? We sum with some z to the volume, and the volume you have to. Of course, the volume of this is infinite, but if you subtract the cylinder, if you subtract the cylinder over precision, the volume is finite, so you can make sense. And then there's some, stuff. Just the natural analog. You can imagine it's a natural analog of what you saw before. We'll talk about it in a second. And then that's a very interesting function. It depends what. So our tuple of partitions is an element. So this is this whole thing. Is an element in a product of Fock spaces. So because partition is the base of Fock space, so it will maybe an element in some Fock space. And since the parameter A1 is attached to the first partition, I write A1 tensor Fock space with the parameter A2. And will be a Fock space with the parameter A3. And it's, like I said, it's very, very interesting what this function is, even for one. So in Nikita's situation, if you had one partition, it was not a very interesting function. Here, even for one partition, it's already a very interesting function.
Maybe you have AR, otherwise
AR, right. Thank you. AR. And this object, so what is this? This is a solution. And now my choice of variables will come to haunt me. I'll write QKZ. But this Q is T3. For what? For the Leo, for something like you take U, H bar, where H bar is, well, depending on your notation, is more or less T1 times T2 of double loops into GL1 double loops. And now I have to explain, since it's my lectures are supposed to be, somehow I'm supposed to explain things. I have to explain with all, where is the father of QKZ? Okay, in his absence, I will explain what this equation is. So QKZ is maybe one of the, and so there's associated with QKZ, there's some other system of difference equation, which is also very important, and the corresponding dynamical equations. In the variable z. So what is QKZ? So if you write QKZ in its full glory, it will take many, many pages, even the simplest example. But if you write it represented graphically, it can be. So in fact, Pasha Yesenkov likes to say that QKZ is the definition of QKZ is the equation that cannot be written on a single page of an Ocidi-Gladek page. But if you do it pictorially, you can write it. So what are the ingredients in QKZ? In QKZ, you need two vector spaces with labels, and you need associated to this two vector spaces, you need an operator, maybe V1 of A1, V2 of A2, and you have an operator from their tensor product to their tensor product. Okay, that's called the R matrix. So this is called R matrix. And now imagine we have a cylinder. And we have some of these strands. So we have some collection of representation, VA1, VA2, and so forth, VAR, some collection of representation with V1, V2, VR. They don't have to be the same. And all of them, except for one, are innocent bystanders. So they all just, nothing happens to them. Well, this one of them, in this case the second, that makes, so when you write R matrices, this thing is oriented. May have further symmetries that allows you to somehow change orientation, but it is oriented. It's so this go straight, nothing happens to them, but one of them makes the tour of the world, goes through, and then comes back here. Clear? This would mean what? This means I act by the R matrix. You know, every time I have a cross, I act by an R matrix, and so this would be a product. This is a product. What's written here is a product of R minus 1 R matrices. And now, in life or in experimental physics, anytime you have a cylinder, you know, if you go around something, it may not be quite periodic. You know, you may come back not quite the same person as you were at the beginning. Maybe wiser, maybe you learned something, maybe not. So this is to say that in any system like this, you're allowed to have another operator that tells you what happens to your space as it crosses this line. There's some kind of operator that you're allowed to have to cross the line. So maybe I don't need a name for this operator right now. But what I do need is I need this operator. So my R matrices always enter this cut from this side. So what I need to be able to do is I need to be able to bring, I need kind of like a Young-Baxter equation, but this says you can bring this crossing from before or after. Right? So this is to say, acting in the tensor product of two representations, this operator commutes with the R matrix. Okay? And so what's an example of such operator? The R matrix in general could be arbitrary function. But in our situation, it will be a function only of the ratio. So as an example of such operator, you can take, for instance, you can make this operator to be a shift. So you had some, right? So this is, yeah, it's just right. So phi, I put like that. So this is my V1 of A, or V of A. This is what is this? This is a function of A with values in V. Well, I can shift it. It's a difference operator. Right? So since the matrix depends only on the differences, this is written a difference operator. And also I can act by any element. I can act by any element. I'll write Z capital. This is representation. This is representation of some quantum group, so I can act by some element. And what I require from this element, the condition. So I require that this depends only on the ratio. So this shift commutes. And now if I want to have this expression, well, that means Z tensor Z has to commute with the R matrix. Right? So what are the elements that commute with the R matrix? So if you think about in a quantum group, well, if you don't know what a quantum group is, no problem. I'll explain it in a second. Well, I'll try to explain it in a second. But the elements, there are not so many elements in the group that satisfy this condition. But there's, so for example, you can take element from Z could be element in the Cartan subgroup. Cartan subgroup. Kind of like the maximal torus. So if quantum group has the maximal torus, and an element in the maximal torus satisfies this condition. And this group here, well, its maximal torus is in some sense one-dimensional. Somehow think about it. This is in the end, one by one matrices up to some loops and so forth. This is really one element here. In the Z, for us, Z, the big Z, little z in the Cartan, this is an element in the Cartan subgroup of this UH bar GL1 at head acts by roughly Z to the volume. So it acts in, this is a grading operator. And how it acts in a Fock space, it acts multiply this element by Z to this volume. So this is how the variable Z enters this equation. Yeah, exactly. Exactly, yeah. Right, so now we have, so this group depends on parameters. T1, T2. T3 is the step. A1s are the points where I have my Fock spaces. And Z is the element Cartan, so we have now explanation for every single variable in this formula. And now, if you think about it, like for instance, well, what does it say? If you unravel this equation, is QKZ.
Can I ask you a question real quick?
Maybe, yeah. If I can understand it.
Yeah. So this, in your picture, these curves are set theoretically only supported on epsilon 3 axis, but not the other two, right? Only one axis.
Right.
Okay.
Yeah. Oh, good. Was good audio. So if you write this equation in its full glory, well, so in general, so this is somehow in general a Q difference equation, a linear Q difference equation. Equation has the form is of the form that I have some. So this is some vector in some space. So I have some vector Z. Maybe that was a bad idea to denote this partition function Z, but maybe too late. Maybe call it. Let's call it. There's too many Z's otherwise. Let's call it capital. We did use this thing, so let's call it psi. That like a wave function. That. So psi of, so what's going to happen? We shift some a, some kind of, in this case we take a2 and we shift it by a1, then we put q a2, and this, like I said, q is t3. And then a3, and then whatever, all variables. This means you apply some kind of matrix that depends on all variables to this element psi of A1, A2, A3. Right? So I shift by, so actual geometric shift is by T3, but I don't want to consider T3 difference equations. I want to say Q difference equation. And so geometrically, what happens? Geometrically, this is an integral, some kind of push for some kind of genus of some space. Genus of some space. Or not union space. Some kind of disjoint union spaces. And then we form generating, when we take the generating function, we sum them up, sum with z to the volume. Right? So z things with different volume belong to different moduli spaces, so we just sum up over that kind of data. That makes sense, right? So this moduli space has connected component corresponding to degree of the curve. The degree of the curve is fixed by the size of these partitions, and then further by the volume of this object. So this, like in Nikita's case, partitions of different size, they belong to different moduli spaces. And what happens here is these spaces break up. So the space break up. And you get this computation. So you have some genus of some space, you can break this space in pieces, and you find some relation of that kind. Now we had many computations. This is a very complicated spaces, but we had many computations of that kind, where you can imagine there's break the space, you can compute the genus. But so if you look here, so this in principle, so if you think of this matrix, this in principle be object of the same nature. You have a countably many spaces, and you sum them up, sum the contribution, all of them up with some parameter, which is like that. But if you look at QKZ, the matrix elements of QKZ, these are QKZ equations are monomial in Z. Z is a diagonal matrix with monomial eigenvalues. So so in this equation you multiply by diagonal matrix. Right? So this means every matrix element is going to be monomial in Z. Just extremely remarkable statement. What means in this computation, a million quadrillion thing has to be equal to 0 for this to be true. Is that what I'm trying to say? So suppose you have, let me say it one more time. So this object is some series in Z. This object some series in Z. If you write the ratio, you expect this series to be the rate, say, right, one matrix series, the other matrix series. Divide by another, you expect this to be series, but in fact it's a monomial. Every matrix coefficient is a monomial. Means some extremely strong statement. So yes, please. This is a vector valued function, but if you take, this is instead of a vector valued function, you can take the corresponding fundamental solution. It will be a matrix valued function. And then if you have two fundamental solutions, if you have a fundamental solution, you can find the coefficient matrix of your equation by just, taking this matrix and multiplying by the inverse of that matrix. And so you have two things which are series, matrices form a series, take the ratio, they're monomials. That make sense? But whatever they are matrix, if you write it in this form, every matrix coefficient is monomial. Which is, I mean, in QKZ, maybe you don't appreciate this fact, but if you think of geometric interpretation, that's an extremely remarkable fact. Yeah. Say it again? Right, but Z is some, it's some kind of grading operator, right? This is like, in conformal field theory, it's like Z, Z is like Z to the L naught. Yeah, so this is some kind of grading operator that acts in a, like normal, somehow usual base, it acts diagonal, right? Means when you multiply the matrix and it's going to look, this will be monomial. Yeah, exactly, yeah. Yeah, I mean, it's in KZ, it's obvious. No, in KZ, it's an obvious feature. It's just some conservation law. But the fact if you write it geometrically, it means a lot of vanishing. And this vanishing, so this kind of the vanishing is kind of the key. The vanishing, this vanishing is super important. Because it's, so people say when they count like actual, when you count objects like this, people say they do some quantum algebraic geometry. They count curves. Right? Well, I don't mean it's an honorable thing. I mean, I'm not saying just mean the word quantum is so overused. Yeah, but somehow you really count things, and that means you there's like the simplest contribution, then the next contribution, then the next contribution. But here, if you look at this expression, it's only the lowest contribution, only kind of like the constant things contribute. Right? So this means this vanishing means your quantum contribution is in fact classical. Yeah. No. No, that's not length space and it's not central charge. So, and this comes, so in other words, you're doing some quantum computation in the sense of algebraic geometry. You somehow, sum over some kind of non-trivial curve somewhere. But in the end, it's only the trivial ones, kind of the constant math contribute. So this vanishing. This comes from rigidity. You have to use rigidity. And it's kind of the use of rigidity here is the key thing. So this is like where the kind of rigidity idea is. Now what sort of rigidity can we use here? So this rigidity, I remind you, so this for this kind of a T here, it's a Bruch rigidity. In K theory is always okay. For any kind of manifold. And so in K theory, this works. It works in cohomology, works in K theory beautifully. In elliptic cohomology, it's not going to be like that, because so in elliptic cohomology, what you need is so in K theory, so this computation is why this computation totally works. Works for some construction. I didn't tell you what's the R matrix yet, right? So because it's easy to say let R be an operator, but then you have to say something about what that is the operator for some construction on the R matrix. And then if we have, hopefully I'll have time to say something about the construction of this R matrix. And so Krichever rigidity requires Requires what? Requires, oh, it's okay. I was explaining the what's QKZ. So now we can all applaud the inventor. So Krichever rigidity requires what? Requires C1 to be 0 or some number n to divide C1 and then this parameter and parameter, whatever the parameter there is, maybe to the power n b1. Right? So this is, so already in Nikita's lecture yesterday you saw that it's better to think that I'm not kind of applying Krichever genus to some moduli space, but I'm sort of integrating one on some derived moduli space. Right? And so that this is already in Nikita's lecture. The moduli space was smooth, but he put a cotangent bundle on it, and then it became. And then if you think of this as a derived object, then it's something zero-dimensional, and you're computing its fundamental class. And in this case, well, for this sort of moduli we're considering here, that's unavoidable. So if I have my moduli problem, and the tangent space to that will not be some actual, this is not an actual vector space. It's like because this will be some, so in Nikita's situation, we had a smooth manifold and it had a tangent bundle. In this situation, it's a singular object. It doesn't really have a tangent bundle, a cotangent bundle separately, but it has their differences. So this has two terms, so there's some deformations. And then there'll be some abstractions. And in Nikita's lecture already we had this situation when, or in general, Krichever genus is what? You have some bundle, if you have a bundle over any bundle or any sheaf over any manifold, always has an automorphism. You can, if it's a linear object, you can scale it. And so there was this parameter, maybe, what do you say? What are we going to call it? It has to do with the canonical class of C3. So since it has to do with the canonical class, maybe let's call it kappa. Is that? Because if I write k, it will be confusing with many other k. So this is this kappa. So this is my parameter. This is like the parameter of Krichever genus times deformations, but there's time abstractions, but they're in this situation. This is the dual. Do. The space is just like Nikita considered, except it's not separately something this and this. It's the difference is defined. And this is the parameter which is in real life in our particular situation is T1, T2, T3, because that's the canonical class. Has to do with the canonical class. What? Yes, right. Or in that case, C3. In general, if I have some threefold, that will have some canonical class. And this is, right? And so now we'll look at it, and we see that the first Chern class of that, what's it going to be? It's going to be the first Chern class of that minus the first minus the first Chern class of that. So it will be two times the first, whatever. If you can define this, there's no bundle like that. But if there was a bundle, there will be twice the first Chern class of deformations. And with Nikita, we actually proved that this is, you can't, this is defined. There is this bundle does have a square root. And so, in particular, it's not equal to 0, but is divisible by 2. Right? So you can't really do full-fledged Krichever genus for these spaces, but you can have a situation when kappa square is 1, then you can have this. This is what Henry, for those of you who remember what Henry's lecture, so there he was talking about how people in kind of Dance and Thomas theory now explore the properties of this Krichever genus. Unfortunately for this, you have to have that condition. No, there's nothing else. So we will, since you lose a variable here, you lose a variable here. Maybe we will focus on K. Any questions? But this space is certainly not equal to 0. It's certainly not equal to 0. So in Nikita's situation, his modular space to begin with was symplectic. In particular, its first Chern class is 0. No, for this original modular space, this one is symplectic. For this, so this guy. It's even better, it's symplectic. So in particular, first Chern class. So you can have a very meaningful theory of Krichever genera for that. If you want to do it in one dimension up, then you have to do this kind of Krichever genus at -1 called the Witten genus. So you have to do the Witten genus. Yeah, something happened. Namely, something happened that this one is not 0 there for the modular space. Right. So this is just connect with Henry's talk, and there's some kind of doing elliptic genera in this situation for Dance and Thomas theory. This is active field of research. I'm not going to say this. I'm going to talk about the rest of the lecture. I want to talk about how they actually construct R metrics. Yeah. In the central board, I was explaining that QKZ has a very remarkable property. From the point of view, if you think of this is supposed to somehow reflect some geometrical problem, the fact that this quantum variable z enters only monomially, it's an extremely remarkable property. You need to have you have to have almost everything vanish. And this vanishing is proven, before you prove something is 0, you have to prove it's a constant. And this is, once you know some complicated expression is a constant, it's then easy to show, it's sometimes very easy to see it's 0, because you can, in some limit, you can show it's 0.
Why you need GL1 you can directly use quantum groups, right?
That is a quantum group. It's a quantum group. No. What do you mean G? Which G? It is a quantum group. It's just quantum group is directly connected to itself. It's not related to the fact that there's double loops here is important because no, but they will not solve this problem. This problem has a unique solution. The other R matrix, if you ask for, if something solves QKZ for one R matrix, it's not going to solve QKZ for some other R matrix. Right? Because for the reason that if you know solution, you know what the matrix of the equation is. Right? So there's yeah. That's right. If already we were discussing before you came that how sometimes people do not everything by Q with different decorations, but today I tried to somehow because it's particularly confusing in QKZ because in QKZ you think that a lot of people like to study QKZ on level 1, in which case the shift Q, it's a Q difference equation, the shift Q and the quantum group parameter are related. The same variable. But in principle, in QKZ, there's no relation between them. Q in QKZ is a free variable. No. For a given quantum group, you can study QKZ with arbitrary Q. But that relation between the deformation parameter and that Q will happen if you impose level conditions.
They are totally unrelated. Why you believe that? Yes, you can definitely.
Anyhow, I just say for people, it's extremely confusing to denote everything by Q, and it's particularly confusing in the context of QKZ. Because I think the Q difference equation should be a Q difference equation. All the other variables unrelated to that Q have to bear different names. All right. So now the R matrix. R matrix is the beginning of a kind of a old story or long story. So R matrix is something like that. Right? More. What's this? This is, well, if you think of quantum field theory, two particles with internal degrees of freedom in two spaces V1 came together, boom, and then it came out, right? Which is to say that there's a more fundamental operator, namely when they come together and then boom happens, and then composed with this boom decaying into things. That clear? So this is where this is. In fact, this operator is just the transpose of this operator. Right? What? That's right. That's right. And so geometrically, this Fock space here. What is this Fock space? This Fock space is it's some module over this group. Well, what it is equivalent K theory of the Hilbert scheme of points. Right? And more generally, if we want the R-fold tensor product, that's equivalent K theory of sheaves of rank R. So this operator is supposed to be, I take equivalent K theory of sheaves of some, so I'll write M R1. So these are sheaves of rank 1. Or bundles, sheaves, bundles on P2 of rank R1. Tensor equivalent K theory of M R2. And this has to go to equivalent K theory of M R1 plus R2. There is a way to do this operation so that really nothing happens. No boom boom. You just take two objects and you take their direct sum. This is like saying, this particle and this particle, they thought they're going to interact, but in fact they didn't see each other. Right? They just, you take direct sum and then you undo the direct sum. Nothing happens. So you need to have something. You need some kind of, this map has to be somehow non-trivial. And to explain how this is constructed, maybe so what is the locus? So maybe I'll say this. If I take, there is a product of MR1 cross MR2 really does embed into MR1 plus R2 as locus of direct sums. And what does it mean, direct sums? Direct sums means you just takes two things, take two bundles, and form their direct sum. Right? What does it mean, this direct sum? This means these are things that are fixed. This means fixed by by the action. So this is again like in Nikita's lecture yesterday. So on MR, you think there's an action of GLR, but in fact the diagonal acts kind of trivially. Well, acts in a non-interesting way. Well, I keep saying it's very interesting that on every sheaf I have a scaling action, but this means on the moduli of sheaves, every sheaf is fixed by the scale. So this is fixed, but if you scale one separate the other, this is non-trivial. So if I take matrix of the form U, 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 and then 1, 1, 1, so this is a one-dimensional subtorus inside my diagonal matrices with A1 through whatever, so forth, A1, A2, so forth. So this is a fixed locus of this group, which you can also say that these are the, what does it mean fixed by a torus? It means like, i.e. the same as critical points of the moment map for this group. And for this action has a moment map, and something is fixed if it's a critical point, and some kind of energy, and this is if it's a stationary point, and so maybe we'll just talk a little bit abstractly about critical points. Many spaces. So in mathematical physics, some people are somehow ambitious to study actual dynamics. More modest people like I, most of the time study just equilibrium, just the things which are just the minimum of some energy. So many spaces in physics are critical points of some function. What? Where? So we did both. No, but this partition function had a boundary condition. The boundary condition lives on the plane. So you count something in C3, and your boundary condition at infinity. At infinity of C2 is the plane. At infinity of C3, there is a plane C2. And that's so. As a function of the boundary condition, we're doing partition function inside. So we describe the things inside via the difference equation that satisfies function of boundary condition. That makes sense? So like I said, many spaces in interest of mathematical physics, they're naturally defined as critical also of some function. Maybe right? So this is if you have a function that has in particular, to functions, whatever defines your critical locus, you can also add one more function to be the moment map of some torus action. So what such terms are called? They're called twisted masses, is that, or something? Something like that, right? Equivalent parameters, yeah. You add twisted mass. You kind of add, you get a kinetic energy of some kind of rotation. Then you have, suppose I had some, so maybe I'll just draw a model situation, just kind of to be pointing to something. So you can have a situation where for special values of parameter, the critical locus will suddenly jump. This is so maybe let's consider a model situation. You had a function, maybe something your function. So this is a U abusing notation. Maybe I take U to be an element in the Lie, because moment map goes to Lie algebra, to the dual of Lie algebra. So maybe U will be an element in the Lie algebra. So I write U times something, whatever. x1. So this usually absolute values with some. So it's like absolute value. Typical moment map looks like this. Times, again, absolute value of x1 squared minus the absolute value of x2 squared. That sort of thing. Some coordinates on your space. I mean, a torus acts on some space. And right now we have an abstract discussion about torus acting on some space. and so in that situation we can add the moment map to whatever the critical locus was. And so then I'll have so if it, function will look something like that. And then this is for this is for u bigger than 0. This will look like that. For u equal to 0, it becomes flat. And for u less than 0, it curls in the opposite direction. And so you want to have a map from here to there going through here. So this is from we want to K theory of the fixed set. Fixed locus to K theory of the ambient space. And then this kind of transpose. I'll just write it. Have this map, and I transpose, because the others are actually K theory of the fixed locus. I said nothing so far. I've just said that we want this kind of map, but if you want the physical interpretation of that map, you may think about it as I had some term in the potential that changes sign, and my critical locus, all of a sudden there's a change. What was the minimum became maximum, and what was maximum become minimum. Right? Well, you think exactly. Then you get, if you go this whole decomposition of this would be the R matrix. All right. And so physically it's it's pretty clear what sort of thing you should consider. That if you should consider, what could be if you're in this equilibrium position, maybe you have your ball. There's some kind of ball here sitting. Well, of course, this ball can roll down. Right? And so you should think of this map. What's it going to look like? It's going to go to, I'm going to kind of map the point here to all points where it can roll down. Somehow, in terms of K theories, you'd say like this: there's a attracting manifold, or whatever downslope How do we say? What's the word for this kind of descending manifold? Is that called it's called descending manifold? Yes. Yeah, somehow descending manifold. And the descending manifold, it projects to the fixed locus because by definition, this descending manifold is something that grows out of fixed locus. So then you know where's the stable, whatever stable manifold. Exactly. Yeah. So this is a project. There's a natural projection. So this is projection. And this is inclusion. So you can think that you would like to maybe in terms of K theory the kind of map. So maybe projection P, inclusion iota. You would say, well, let's say I do P pull back, iota push forward. Something like that. It's not the actual formula, but otherwise it'd be kind of simple if it was the actual formula. So what's the both geometric and mathematical difficulty with this definition? And the physical and geometric and physical difficulty with the definition is this descending manifold, this stable manifold. It's not closed in the ambient space. This is not a closed inclusion. There's no push forward here, really, because it's kind of locally closed. But if I let this ball roll, if it rolls, it might very well roll to a different position, a different stable such configuration. It will roll down to some other position. You can have this kind of Morse trajectory, soliton, something, right? So that's, in other words, this guy here, what I'm trying to say, this guy here, this is not closed. And those of you who went to the exercises, we looked at the simplest examples of this sort of things. The simple examples of this kind of things are like Schubert cells. Schubert cells, it starts as stable manifold for something, and then if you close it, then stuff happens. Who knows what's in the closure? What this thing looks in the closure? And in general, in algebraic geometry, it's okay to take the closure for abstract reasoning, but not in any concrete situation, because you never know what's in the closure. Right? And you don't. And even if you knew what's in the closure, that would be something horribly singular. It will not have, somehow, will not. This would not be a nice map. Instead, the best way to deal with this issue is the following. So this is, you can explain historical, you can explain explain this in why you come to such definitions. Maybe there's some kind of historical explanation, but it may be easier to just start from the end. Starting from the end, the exact same thing we can write in elliptic cohomology. So we can think of elliptic cohomology of fixed locus you want to start with go to elliptic cohomology of ambient space. space. This is what? So we don't. This is elliptic cohomology. Like I said, this is maybe this notation slightly misleading, because there's no elliptic cohomology ring. What we would like to say, from this is a map from line bundle here to line bundle here. So this is a section. So this thing is a section of some line bundle. In fact, some theta bundle. Some theta bundle. Because push forward, push forward involves theta bundle, so it's a section, some line, some kind of theta bundle. Theta bundle, which we know near one fixed point, one component, of the fixed locus, and wish to extend. Yeah, because a sheaf of rings is not a ring. So this is not it's not so particular abstract. This is not so super abstract, because remember we had this picture. Yes, I'm not going to try to redraw the picture from yesterday, but maybe schematically redraw it. Remember, what was for instance, we would look at the elliptic cohomology, equivariant elliptic cohomology of, say, I don't know, let's say P, what would you have? P2 or Pn. Pn. What was that? That had some variables. A, and so this is, and over this is elliptic cohomology of a point. And then a bunch of, I draw them as linear subspaces, but they're they are abelian varieties, so they look something like that. Given by the equation that this variable t is equal to one of the AIs. And they intersect where this A over. So maybe when this was, maybe let's say there's a t equals maybe A0 inverse here t equals AI inverse, here t equals AJ inverse, and there where AI is equal AJ, these two things intersect. That makes sense? So suppose we start at the top. At the top, we know so maybe this is, so in our projective space has n, so maybe n plus one fixed point. This was where t equals A not inverse. This is t equals A1 inverse, and the attracting order is going this way. So suppose we start at the top. At the top here, we start here. And here is this. Here we know. Here we just look this at iota push forward or p pull back. Section of some line bundle. Now, suppose we come, so we come to the, and right. So then we come to the next fixed point. Maybe we come to some other fixed point. Then we do them in order. We come to the next fixed point. Then there we're supposed to reconstruct a section of some line bundle from what? So we come to, let's say, we come to the second one. So let's say T equals A1 inverse. Here, what do we know? It's a section of some line bundle which we already know, or the intersection with the first one. And we know also a little bit more about it. So we know that we also know, right. This is supported. This is section some line, but more importantly, supported. This is important. Supported on full stable, full attracting locus. So this is maybe we should think of this as seating. This is to make things symplectic. Maybe we should think of this as seating inside of its cotangent bundle. This would be. And so we start with something which was supported. So we start with a section that was supported. So it's always right. In this picture, I kind of assume, the fact that the attracting and repelling, they always balance, kind of assumes in this discussion that there's something like a symplectic thing going on. So we started with a section which was already supported on Pn itself. Right? So that says about this section on the next thing we know what it equals at this point, and we also know, so we know the value. Know the value here. Here by induction. And know some vanishing. Plus vanishing from support. Condition. So if you know enough about a section of a line bundle on the abelian variety, you reconstruct it uniquely. And make sense? What? Well, it's normalized there. So what? No. This has nothing to do with the R matrix. This is spaces of some dimension. They're not lines. Yeah. This is schematic representation of the kind of picture that we had. This picture that was here for half of yesterday's lecture. A bunch of linear subspaces that intersect in some condition. So what is it? Somehow, just completely abstractly. Suppose I have. What would you like for an arbitrary algebraic variety? What would you like a letter for an algebraic variety? What? V. No, that's a vector bundle. That's called Y. Let's call Y. So Y is algebraic variety. And L line bundle. D. So these things, so this is a codimension 1 condition. The things intersect in codimension 1. So this is D divisor. So you can you look at sections of on your Y of your line bundle L. You can restrict them to the divisor. And so this is to the divisor line bundle L. And there is what vanishes under this map are what vanish on this map? This is sections of the line bundle that vanish on the divisor. So these are the sections of the Y, the line bundle shifted by the divisor. Done. And then this may not be surjective. There, in principle, could be a connecting map to H1. So forth. Now, what does it mean what does it mean interpolation problem? Interpolation problem is reversing this error. Right? You have a section defined on the divisor. You would like to lift it to section defined on the whole variety. Right? So you have a polynomial in two variables, which you know when it's restricted to a curve. Then you have to reconstruct, you're trying to reconstruct the polynomial to variables from its restriction to a curve. Right? So you're trying to reverse this map. So the co-kernel of this map, so this kernel of this map goes here. So these are obstructions to interpolation. And this is, of course, and this thing is ambiguity in interpolation. Right? Because if you have some section just vanishes on the divisor, I'll just go to 0, right? So to have a unique solution of interpolation problem, you would like this group. You would like this group to vanish. So, how to say? This is mathematical notation that you would like this to happen. And you would like this to happen. Right? So if this two thing happens, then the interpolation has unique solution. It may still be, this. I mean, if this is not 0, then it never has a unique solution. But this, there's this thing. Well, anyhow, there may be a unique solution even if the group's non-zero. But somehow, we would like this condition. Now. No. This is not what we're going to do. We're going to do something else. So we will, in the exercises, I don't think you guys got to that part yesterday, but in exercises, one has to prove that if I have an R for R case, So for us, Y is an abelian variety. Product of elliptic curves, but what I'm going to say is true for any abelian variety. So L and Z, well, they're line bundles, some kind of theta bundles. Both some kind of thetas. What we're going to use? We're going to use that if the degree of D, or the degree of the line bundle. So what we would like? We would like the degree of L minus D to be 0. If this line bundle has degree 0, which is not a numerical condition, it's a condition. So if a product of n elliptic curve, then it's like n choose 2 conditions. Because again, in exercises, somehow line bundles on the product of elliptic curves are parameterized by symmetric matrices. And this condition, this is some sort of some kind of this is some kind of balance. This is some kind of balance that comes from, in these applications, come from symplectic form. On your original variety, we had some original variety, maybe call it X. So if I have a degree 0 line bundle with the curve, there's a dichotomy. So then there's 2 possibilities. Either L minus D is trivial, or cohomology of every single cohomology group of this thing is 0. So this is something so I don't think we're going to get to that in exercises, but you can, there's in exercises, you can work through them, you can prove this. And so this looks good. Except, so this would say that this problem will have unique solution most of the time, except we have to worry about the situation. This is some kind of resonance. That we have to avoid. And that resonance you see in this formula. In every single formula, like not every, almost every lecture in this workshop has to have this formula. You look theta of x times z over theta of x times theta of z. What is this formula? This formula is this is a formula. This is interpolation of the function 1 from 0 elliptic curve to the whole elliptic curve. Right? You're looking for a problem. You have a function 1 at the origin. You would like to find a section of a line bundle of degrees, a section of suitable line bundle that, or from 1. Section of certain line bundle that interpolates this. But you see in this formula there's a denominator, right? So there's this guy here. So it means, and this is why, because if I have a trivial line bundle, then something else happens. That makes sense? And so this is, you need some variable like so. So if you're solving interpolation problem, if you're solving interpolation problem for fixed line bundle, you may very well be in trouble because it may be the case that if you come down sufficiently far away, you're going to hit a resonance, you're going to hit a pole, and then you'll be dividing by 0. But if you, from the beginning, from this problem, you introduce this variable z, so make this line bundle vary. So whatever line bundle you have, you can vary it. So your original line bundle from the very beginning, from here. Instead of solving it for fixed line bundle, you can solve them from all line bundles at the same time. You can think of this as you can twist by an arbitrary degree 0 line bundle, because if I twist everything by an arbitrary degree 0 line bundle, nothing is going to change. So I take peak 0 of the elliptic cohomology. Well, who knows what this is, but it always maps. There's always subset here. There's always subset here, which is formed by first Chern classes of line bundles. So there's always peak of x itself tensor your elliptic curve. This comes from the, if I have a line bundle, it has a first Chern class. If that first Chern class, I can make a degree 0 line bundle here. Right? And so here you introduce this variable z here. In this variable z, these are the dynamical variables. In the quantum group, in the quantum group language. Groups. And also, right, everything's. And also, there's the same z. The z come from peak of x. Also the z, so this is also z from kind of this kind of z volume. People call them Kähler. And then they demonstrate their full glory if, well, I have 1 minute. So this is, maybe I'll try to say what I was saying one more time, and then I just say where are you going to see the z come back? Is that this is, we introduce at this stage, we introduce them so that not to worry about poles. Because if I multiply by generic degree 0 line bundle, then the whole thing works through, and it's just like that z over there. But where is it gonna? So they come back if I want to know. I had this function psi of a bunch of partitions, kind of elements. So it's an element in Fock tensor Fock. I'll just write inside Fock R-fold R-fold tensor product, depending on the variable A1 through AR, T1, T2, T3, Z. This was solving QKZ, but from geometric considerations, I can also say, I can not just say it solves QKZ, I can make the solution more explicit. I can say, well, it's in fact an integral of something, some kind of rational expression, rational function, times elliptic function, times a product of some kind of Q gamma over Q gamma. And the meaning in conventional language of UKZ, this is the off-shell beta function. Beta. This is like in Collis. And well, we're going through various Collis Seminole papers. This what produce you the beta equations. This is the Atawara of the beta equations. And this, you think, what good it is to have an elliptic function here? Because elliptic function is something which is Q constant, right? So this is the analog. So instead of you solving a Q difference equation, then you can stick elliptic function under the integration sign. This is the analog of contour of integration. Integration. You don't have to move. So usually when trying to solve equation, you kind of choose different contours of integration. If you solve a Q difference equation, this amounts to just, you can stick an elliptic function here. Right? And so this comes from UH bar, whatever, G hat. This is from the elliptic thing. Elliptic quantum group, which you can construct the same way. And the point is that you solving an equation depends on Z. So in this expression, this elliptic quantum group, you have to have those variables. So these variables that are this is the Z to the volume Kähler variables here. They somehow have to come here. And the way they come here is that here they just label elements in peak 0. Okay, so with this, there's some variable, so product. No, that's okay. So how would you like the integration variables to be called? What? Who knows? Phi. Okay. Phi. I wanted the absolute value to be 1. Oh yeah, okay. I know, no. I write d hard and integral over maximal torus and gauge group. No, you start, so you construct this moduli spaces as quotients of something. And so that's the maximal torus there. Similar, yeah. All right. So it's somehow. At the beginning, it feels like 5 lectures is a lot of time, but at the end, it maybe feels like, okay, anyhow. Yeah. What? Well, in our case, this G hat is GL1 double. But in general, there's some kind of G for which you take hat. And I mean, there are many ways to explain why if you try to define an elliptic quantum group, you need more variables. Many ways to say it. But in this formulation, I gave you at least 2. So one of them, because they have to come up somewhere where you, on the one hand, should. Well, anyhow, I'm just repeating myself. Maybe I'll stop here.
Any quick questions for Andrei? Remember, we will have whole 2 hours of exercises and discussions after lunch, but